Hello everyone, welcome back to the SWAM NPTEL course on engineering aspects of biofuels and biomass conversion technologies. I am Professor Ijaz Ahmed, currently Assistant Professor in the Department of Chemical Engineering at IIT ISM Dhanbad. In Module 11 of this course, we are discussing about algal biomass conversion technologies. Particularly, we have discussed the basic introduction of algal biomass, the sources, classification, then we discussed the conversion technologies. Then we discussed the mechanism behind that, but particularly we were limited to the fuel application. In lecture 5 of this course, we will discuss about the chemical production from the algal biomass. So if you look at earlier what we discussed was fuel production from the algal biomass. So we started like we have, if I start the process as a whole soul, so we started like photosynthesis as a step 1. And then in step 2 we did harvesting of algae, and then we have a step 3 where we do the disruption and then we have a step 4 where we learnt about the extraction, and then after this step 5 we discussed conversion, right? Now in this conversion we had different methods like different products. So we can say we made the biodiesel, or you can say transesterification. Then we have fermentation. Then we had anaerobic digestion process. Then we also discussed biohydrogen, bio H2. We also tried to discuss about combustion, pyrolysis, and gasification, right? But none of these processes, and then one more, of course, here the hydrothermal liquefaction process. But none of these processes gives chemical. What they provide is the fuel. Now the question here is, what if we need chemical, then what we will do? And for that, this lecture is very important, that algae is not just about fuel. So as I said, the algae is not about just fuel. Algal biomass can be used to produce pigments, barrens, bioplastics, proteins, polysaccharides, omega 3 fatty acid, and lot of other things that can be produced. In fact, if we have to set up a algal processing unit, it should be an integrated biorefinery kind of thing where we produce fuel as well as chemicals both. Otherwise, we will end up losing lot of money that otherwise we could have earned by making a integrated biorefinery that produces both fuels and chemicals. Now herein, if I talk about what are the major products, so major product I showed you already here: pigments, barrens, bioplastic, proteins, polysaccharides, omega 3 fatty acid. Now let's discuss pigments. Okay, in pigments, these are algae are usually rich in, I would say, algae. So let's say here I have algae. This algae is rich in chlorophyll. Okay, carotenoids, and phycobiliproteins. Okay, for example, spirulina. Okay, this is used for, this is like phycocyanin, used for or it is a blue pigment, you can say it is a blue pigment used for food. Okay. Similarly, we have another example. Okay. This is beta carotene. This is used in food, cosmetics. This is I'm talking about algae pigments. Okay. If you remember the different parts that we cosmetics and provitamin, you can say provitamin. Okay. Then we have red algae. Red algae is used for biomedical research. Biomedical research. Okay. Or sometimes, I mean, overall, we can say the pigments or the pigments has application. Pigments are also natural colors. Okay. Natural colors. Has application in food, food, health supplements, health supplements, and cosmetics, cosmetics, natural dyes, etc. Okay. Similarly, we can have omega-3 fatty acid. Second part is omega-3 fatty acid we can produce. Okay. Now, because some algae synthesizes DHA. Okay. DHA is docosahexaenic acid. Okay. And EPA. Okay. Now this is used in infant formula, nutraceuticals, brain health, heart disease prevention, etc. Okay. This is a sustainable alternative to fish oil. Okay. Now similarly, the third we have is the polysaccharides and hydrocolloids. Okay. Now here, for example, agar this comes from red algae, okay, which is used for microbiology and different applications. Then we have carrageenan. Carrageenan. This is used in ice cream, toothpaste, toothpaste. Then we have alginate. This is used in wound dressing, food gelling agents, etc. Then fourth we have like proteins. and bioactive compounds. Okay, so particularly spirulina and chlorella, 50 to 70% protein by dry weight. Okay, therefore it is used as protein powder, animal feed, aquaculture feed. Okay, then we have applications as, so this was fourth. Fifth, biofertilizers. We can make biofertilizers and biostimulants. Now biofertilizers, for example, seaweed extract improves soil fertility. Soil fertility. Okay. The other is, for example, Scophylum nodosum extracts are widely sold as plant growth promoters. Okay. Sixth is bioplastics and biopolymers. Bioplastics and biopolymers. Okay. For example, algae derived starch and cellulose proteins can make biodegradable plastic. Okay. For example, we have PHA, which is polyhydroxy hydroxy alkanoids produced by bacteria fed with algal biomass. Now the question here is that to make all these products, how do we extract it? So as I said, the simple process for conversion or process for chemical production, of course, preparation is one part. But in general, if you look at the growth, harvesting, disruption, etc. are one part. Step one, if you look at extraction, okay, that can be solvent extraction or any other we have discussed already. Then fermentation or bioconversion. Step 3 can be biorefinery concept, where we can make both the fuel as well as the chemicals from the algal biomass. Okay. Now, why we are interested in chemical is because there is a high value market for the chemicals coming from the algal biofuels or algal biomass. They are renewable in nature. It reduces the CO2 emissions It is eco-friendly, it is alternative to several synthetic chemicals, and then of course it has application in food, pharma, everywhere. Okay. Therefore, this is very important. Okay. As I said in the beginning, that it can be, we can do the thermal conversion, chemical conversion, biological conversion, and if we have algal biomass, triglycerides, free fatty acid, and then we have two routes, decarboxylation and decarbonylation. This is also another important emerging route where, I mean, a lot of attention is given. In fact, lot of linear chain hydrocarbons, sustainable aviation fuel, biopolymers can be made from algae by using these two routes. Okay, so we'll focus on that. If you look at decarboxylation and decarbonylation is one of the most promising routes for producing high value monomer olefins from the algal biomass or free fatty acids or fuel grade hydrocarbons we can produce. This approach is especially relevant now when biofuel sustainability and feasibility face environmental and economic challenges. The progressive oxygen removal via decarboxylation or decarbonylation offers better economic feasibility, efficient processing of third generation feedstock like algae, algal free fatty acids, and then it is very effective for deoxygenation of carboxylic acid from many source and processing of non edible vegetable oils which are rich in free fatty acid. We will also discuss in next week classes about the oils and what we can make from the non edible oil and edible oil in terms of fuel and chemicals. Okay. Particularly, the integration with biomass processing technologies can enable the conversion of organic acids into fuels, value added products, and other things. The chemicals obtained from the decarboxylation and decarbonylation route can be upgraded into polymers, plasticizers, aldehydes, detergents, wax, lubricants, and other things. Therefore, exploring the decarboxylation and decarbonylation route can open a window of new opportunity to achieve the sustainability goals. Okay. Now we'll see here, if you look at the typical reaction, what happens if I have free fatty acid here, it can go via decarboxylation route and we can get linear chain alkane that can get H2 to become alkane, or we can have alkane here, and or we can go via decarbonylation and we get alkene that on hydrogenation gives the alkane. Okay. So if we say removal of carbonyl group from free fatty acids produces CO, CO2, H2O byproducts and alkanes and alkenes. If we talk about the product specific selectivity, as I said, in the decarboxylation, we have directly linear chain alkane, while in decarbonylation, we have alkene. So here, decarbonylation favored for the linear alpha olefins via selective CC bond scission, while the decarbonylation is favored for fuel hydrocarbons, linear alkanes, but then requires extra hydrogen for that. Okay, the reaction mechanism and the catalyst properties plus the process parameters determine what will be the final product selectivity. Thermodynamically, both the reactions are favored above 300 degrees Celsius and produces oxygen-free hydrocarbons in the range of jet fuel, green diesel, with a structural similarity to that of the fossil fuel that you can also see here, which is obvious. Okay. Similarly, there are potential emerging areas like we can make linear alpha olefins monomer, which are monomer for the commodity chemicals, and then there are other products that we can make through it. Okay. If we talk about the other products, so one is the decarboxylation and decarbonylation route to produce the linear chain alkanes or alkenes. Similarly, we can also produce linear chain hydrocarbons from the algal biomass via other routes. For example, the hydrodeoxygenation that involves again the hydrogenation of the double bonds that converts the unsaturated fatty acids into the saturated, then CC bond cleavage that shortens the long carbon chains, and that is followed by oxygen removal, of course, via decarboxylation or decarbonylation. or direct deoxygenation as well. So herein, what we need is a catalyst, and if the name itself suggests hydrodeoxygenation, that means we need hydrogen. So we have high temperature requirement, high pressure, and catalyst, particularly noble metal or transitional metal or zeolite catalyst, to proceed for this reaction. And once the oxygen is removed, the end product we get is liquid, which is diesel and hydrocarbon gases, which are CO, CO2, methane, and propane. Okay. Current transport fuels uses the linear hydrocarbons, unlike oxygen-rich algal biomass. Therefore, the removal of oxygen becomes very important. Okay. Otherwise, it cannot be used directly as a fuel. Particularly, the triglycerides from the algae can be upgraded via hydrodeoxygenation that can produce C13 to C20 hydrocarbons, which is particularly diesel range, identical to fossil diesel. Or we can do selective cracking, reforming, hydrocracking to make jet fuel as well. Okay. Now, this processing, as I said, generally happens in two steps. The one is the first extract the triglycerides or bioil from the algae, and then you do the hydrodeoxygenation. Okay. There are good potential to integrate it with the pyrolysis and liquefaction. So we'll get the algal oil, and the algal oil will be catalytically upgraded, or we can put the catalyst itself during the pyrolysis process or the algae process. For future respects, we can also try the one pot hydrodeoxygenation directly from the algal biomass. Okay, and that may be a good option for the future, and I think that will be very helpful. Besides that, we can also produce the aromatic from the algal biomass, and that gasoline contains aromatics plus light hydrocarbons. Okay, but the algals usually yield the oxygenates and diesel. So what we need, again, a catalyst. Okay, and it is very important because these aromatics actually are the octane enhancer. These are key, and also the key petrochemicals for the plastic and solvents. Okay, so what we do, we try to focus on oxygen free aromatics, and then there are, I mean, although it is very emerging and there are different methods by which you can do it, but still you can try to make it. For example, if you use a zeolite first to convert to linear chain alkane, then you can use a zeolite to convert these linear chain alkanes into the aromatic form. Besides that, we can make polymers. So for example, as I said, that let's say we have free fatty acid coming from algae. There are two possibilities. If I give H2 via decarboxylation, I can get linear chain alkane, right? Or if I go via decarbonylation, what I'll get is, now this has a double bond. That means we can use it to make a wide range of polymers or biodegradable polymers as well. We can use it to make a wide range of biodegradable polymers as well. So there are a lot of opportunities that can be done with the algal biomass, and I believe that there are other routes as well, but primarily what you have to remember here, that the whole process starts with the growth, followed by harvesting, followed by disruption. Okay, that is followed by extraction, that is followed by conversion. Now the conversion can be chemical, bio, or catalytic. After the harvesting, we can use the high temperature process as well. But if we have to go for low temperature, we'll have to go through this process. So this is all for today's class. See you in the next class. Thank you.